This talk is on controllable power sources and their applications for harvesting solar energy and transportation. Our company is Holtzman Inc. in Longmont, Colorado, USA. We specialize in inventions for reducing global warming. I will be showing you applications for a little-known circuit element called a constant power source. This circuit element should have practical applications. For example, harvesting solar and wind energy and extending the range of electric cars. This material assumes some knowledge of electricity and solar energy systems, and I will try to make it as simple as I can. In circuit modeling there are a couple of well-known elements: an ideal voltage source and an ideal current source. An ideal voltage source will always deliver a same controlled voltage, such as 12 volts. By always, I mean a connected load or how much current the load draws does not matter. Voltage is current times resistance. This is Ohm's law. V equals I times R. Power is voltage times current, and energy is power multiplied by time. So current is voltage divided by resistance. I equals V divided by R. If you short out an ideal voltage source with a value of R that is 0, current can theoretically go to infinity. If you short out the voltage source with a low resistance bare wire, it will get hot and burn you if you touch it. Ideal voltage sources do not exist, but a large battery with a low internal resistance, such as a car battery, is a fair approximation. Here is a plot of voltage versus current for an ideal voltage source. Voltage is a vertical line. Since R equals V divided by I, you can draw in what is called a load line with a slope of 1 divided by R to find an intersection, which is an operating point. On the other hand, here is a plot of an ideal current source. It will always deliver a same current no matter what load it is connected to. For example, an ideal current source could be 10 amps. V equals I times R, so if you leave this ideal current source open circuited with R equals infinity, the voltage can theoretically be infinite. If you leave a current source open circuited, it can electrocute you with infinite voltage. A good current-regulated power supply, which is set for a high voltage and a limited current delivery, is an approximation of a current source. A LT3902 integrated circuit is one example of a two-terminal programmable current source. This graph illustrates a constant current and a load line, showing an intersection which makes another operating point. This is a plot of constant power shown as voltage versus current. What I am showing today is a controllable power source which always delivers a controlled power into whatever value load you attach to it. Power depends only on a control level, which could be a voltage, a current, or a digital number. P equals V times I. So if current is high, voltage will be low, and if voltage is high, current will be low. And here is a plot of two different powers, a stronger red one and a weaker blue one. There are also a couple of load lines, a green one for high resistance and a yellow one for lower resistance. The output voltage and output currents cannot be controlled. The exact desired power will be delivered at the voltage and current values where the load lines intersect the power curves. This delivery holds until a circuit hits its current or voltage limits. How would you build such a power source, and what are some applications? One way is to use a Maxim Max 4210E integrated circuit. Another is to modify a switching power supply to deliver controlled power. One way to build this controlled power source to charge up an inductor to a controlled peak current from a power source on the left and then let it discharge into a load on the right. The switch moves between positions C and D. Inductor energy equals 1/2 of the inductance times the peak current squared. If you repeat this cycle at a fixed rate, a fixed controlled power will be delivered to a load, because an energy delivery rate is power. What the load is does not matter. Could be resistive, like a heating element, or another power source, like another battery being charged. A delivery rate of 1 joule of energy per second gets you 1 watt of power. Now I want to talk about making solar panels work together with maximum efficiency. For the Northern Hemisphere, an ideal static solar installation is one with all panels facing south and tilted at an optimal angle. The angle depends on latitude, and there should be no shading. All the identical panels want to receive a same illumination. Unfortunately, this may not be practical for all installations. For maximum power output, each solar panel in an array should be maintained at what is called its maximum power point, or MPP. This maximum power tracking voltage will only be the same if all panels wired together in an array of panels are of identical design, operating at a same temperature, and receiving identical illumination. This colorful graph shows the current versus voltage for a solar cell at different illumination levels. When the sun gets brighter, current goes up. The rising line intersecting the knees of each curves is the MPP. This graph shows amps versus voltage in red and watts versus voltage in blue. This illustrates a maximum power point for a solar cell at one illumination. The point at the peak of the blue power curve is the maximum power point. A tracking circuit needs to track this peak point as conditions, such as lighting and temperature, change. If MPP is being tracked for a group of panels wired together, they all need to match with the same illumination. Otherwise, efficiency falls. There is also one more challenge with individual solar cells wired inside a solar panel. If you put many cells in series, the weakest one's current determines a string's current. Each silicon cell only delivers about 0.6 volts, and many are wired in series to get the panel's voltage up to around 20 volts or so. This is a SPICE circuit simulation of a solar panel with only 2 solar cells. Each cell is modeled as a current source in parallel with a silicon diode. Over a 1-second modeling time, the voltage on the V1 load increases from 0 to 2 volts, shown as a green trace. The bottom cell's current source has a steady current of 10 amps. The top cell has a steady current source of only 5 amps, perhaps because there is a leaf over one solar cell. The result is that the load's V1 current, shown as a red trace, follows the bad top cell at 5 amps. If a chain of many solar cells in series has a weak cell, the weak cell determines the delivered current for the solar panel. A string of solar panels on your roof can have 20 to 30 panels wired in series. In an attempt to get around this problem, solar panels normally have built-in bypass diodes that bridge strings of cells with one or more non-producing elements. Solar energy has gotten very cheap, largely due to excellent design and manufacturing ability of Chinese manufacturers. Improvements still continue, but as of about 5 years ago, they became a cheaper energy source than a coal or gas fossil fuel power plant. Now there are also bifacial panels that can absorb power from both sides of a panel. It is practical to use a vertically mounted solar panel with a front side facing east to catch the rising morning sun and the back side facing west to catch the setting afternoon sun. Solar panels are now cheap enough for roofing or privacy fencing. But combining power from these different panels with differing illuminations is a real challenge because they all have different MPPs. In Europe, balcony solar systems are now being sold. A renter hangs solar panels over their balcony rail and plugs them into the apartment's wall outlet through a grid tie inverter. One solution to a blockage problem is to wire solar panels in series and bypass any panel that is limiting the string. Devices doing this are called optimizers, and SolarEdge and Tigo are vendors. Another solution is to put a microinverter with each panel and convert the panel's DC to AC. Each 230 VAC inverter output is then connected in parallel. Enphase is a vendor of microinverters. These devices are located under the solar panels on the roof. This diagram shows what an installer might like to do. Have 2 south-facing panels directly connected to a grid tie inverter, but add to that same grid tie inverter a couple of panels facing the east to catch the rising sun and a couple of panels facing west to catch the setting sun. The inverter is tracking the MPP of the south-facing panels, but the east and west panels are connected through new devices called switching power converters, or SPC, to adapt the DC energy from what the panels want to produce to what the inverter's bus is operating at. A controlled power source can be the SPC. These plots show how that works. A first voltage versus power curve A is for the unconditioned south-facing solar panels. The second curve B is illustrated as a dashed line. It is for the panels that are facing east or west and using a SPC. This B curve is nearly flat because power delivered is constant and independent of load voltage. That said, a voltage limiter keeps voltage from going beyond a safe limit. Curve C is curve A added to curve B because of their parallel connections. A grid tie inverter will track the MPP combined point. Diagram of my patio solar array with 3 solar panels. 2 of the 18-volt solar panels are wired in series and connected to a 36 DC input on the grid tie inverter. The SPC converts the input 18 volts from a single panel to whatever DC input voltage the grid tie inverter runs at, usually around 36 volts. This voltage varies because the MPP on the grid tie inverter oscillates looking for a peak power. But the SBC does not care about its output voltage. The SBC is delivering MPP for its host panel. Here is a picture of the 3 panels delivering power. The two 195-watt panels on the left are connected in series. The 195-watt panel on the right is using a solar power conditioner. Here is a photo of my prototype patio solar power conditioner. It is a proof of concept device that makes MPP power from a solar panel. A popular Chinese boost converter, 1, was modified to sample peak inductor current and also receive a control input pulse width modulation, PWM, signal from an ESP32 microcomputer. 2. The pulse width determines the inductor charge time. The boost converter runs at 20 kHz. The microcomputer also does MPP tracking and drives a diagnostic screen. 3. A small buck switching regulator located under the display makes 5-volt power for the microprocessor. A prototype board, 4, contains a few components for interfacing between boards. It works well with varying sunlight. Thank you.